We tested two experimental configurations for the shake table tests at UNR. The first was 3-story building with base isolation alone, and the second was base isolation with the added phase damping system, or base isolation with gap damper. We performed several types of trials, sine waves in X and sine waves in Y, for unidirectional characterization of the isolation system, a figure-8 motion for bidirectional characterization. Finally, we executed several earthquake record sequences in the X direction, in the Y direction, and bidirectionally, or in XY. We selected 3 different earthquake records: the 1989 Loma Prieta earthquake, recorded at Los Gatos Presentation Center, or Loma Prieta. This was the best near-fault motion that led to good expected performance of the gap damper system. We selected the 1995 Kobe earthquake at Takatori Station, or Kobe. This motion had strong bidirectional action to test the gap damper performance bidirectionally. And finally, we selected the 2010 Chile earthquake at Concepcion Station, or Chile. This was a longer duration motion. This was a longer duration motion that tested the ability of the gap damper to perform over several cycles. The idea behind the test program was that we scale each earthquake record so that the displacement demand realized by the base isolation configuration was about equal to an over MC displacement of 5.7 inches. This motion was referred to as the 100% target motion. But it was approximate. We had to make some test day adjustments to achieve the displacement demand that we were looking for. And the goal of the base isolation with gap damper configuration was to reduce the displacement demand from 5.7 inches back to the MC displacement of about 4 inches. Now this is what we were expecting when we started designing the experiment, but we didn't have the building design, we didn't have the damper characterization data yet. Once we were able to put everything into our model, we weren't expecting to achieve quite this large of a displacement decrease. And we were expecting more like maybe about 4.5 inches, or a 20% decrease. Throughout the test program, the earthquakes were executed as 3 record sequences scaling up to the 100% target motion. This table shows the planned earthquake scale factors leading up to the 100% target for both unidirectional motion, X or Y, 60%, 80%, and 100%, and for bidirectional motion, or XY motion, 60%, 80%, and 100%. The numbers in the table are the actual scale factors applied to the earthquake records for each target. And you can see that the scale factors are a little bit smaller for XY bidirectional motion compared to unidirectional motion because larger displacement demands were expected. First, we show a representative test from the base isolation configuration. This is 70% of Loma Prieta in the X direction. In fact, we did not run beyond 70% because the experimentally observed displacements far exceeded those that we predicted analytically. You see a video capture on the left and the isolator hysteresis loop being traced out in time on the right. And the peak displacement from this test was about 5.85 inches. This next series of clips show the corresponding Loma Prieta 70% in X direction excitation for the base isolation with gap damper configuration. The first clip shows a close-up of the gap damper system on the left and the damper time history being traced out on the right. There's a large spike every time the damper is activated. So this is a relatively short motion that only activated the damper a couple of times. This video shows the same view of the gap damper configuration on the left and the damper hysteresis loop being traced out on the right. So this shows the energy dissipation being provided by the additional damping. The next couple of clips focus on the motion of the isolator. Show the isolator movement on the left. On the right, we show the isolator displacement history. The blue is for the base isolation configuration, and it's traced over by the displacement for the system in the gap damper configuration. And you can see the reduction in displacement demand that is being provided by the phase damping. Similarly, we look at the isolator hysteresis loop, base isolation in blue, Base isolation with phase damping, traced out in red. And again, note the displacement reduction. To summarize, the displacement demands for base isolation alone, 5.85 inches. When the gap damping is added, it was reduced to 4.97 inches, which is a 15% reduction. Finally, one might wonder how the additional damping affects the accelerations in the building. Here we look at the roof acceleration with the isolation configuration in blue, the gap damper configuration being traced over in red. So you see acceleration spikes when the damping is activated. However, they still aren't particularly large as the total acceleration is less than 1g. To summarize, the peak acceleration for base isolation was 0.35 g, which is very low for a large earthquake like this. When we add the gap damping, we can still keep the acceleration below 1g. The next series of clips are for Loma Prieta 100% in XY. This is a bidirectional motion, and so here we can see the contrast between unidirectional and bidirectional. This first clip shows the motion of the damping system, activation of the damper. It was actually very similar to what we saw in the X direction, as there wasn't a whole lot of Y direction motion for this particular record. The isolator displacement history, the isolator displacement trace. This is displacement in X versus displacement in Y. Again, blue for base isolation, red for the system with gap damping. There was not quite as much of a reduction of the displacement in this case. For base isolation alone, 5.59 inches. For base isolation with gap damper, we had 5.03 inches, about a 10% reduction. Finally, the roof acceleration in this case. It's very similar to what we saw for X direction only. Acceleration spikes when the dampers are activated. The peak accelerations are similar to what we saw in the unidirectional case as well. Next, we show a couple of tables that summarize the results for isolator displacement. For each earthquake, record, and sequence that we ran, we show the displacement for base isolation, the displacement for base isolation with gap damping, and a percent reduction. This particular table is for X direction motion. As we look at the numbers, we make a couple of observations. First, the percent reduction in displacement tends to increase as we get closer to the 100% target. This is what we expected because this is the level of excitation that the gap damping system was designed for. Second, we noticed that the gap damper was more effective for the Loma Prieta motion than for the other motions. This also agrees with our analysis, although we don't have a good feel for why at the moment. The Kobe motion seemed to be similar for unidirectional. The Chile motion, for which the gap damper was the least effective, was a long-duration multi-cycle motion. This is a similar table for bidirectional or XY motions. In general, the gap damping was less effective for bidirectional motions than it was for unidirectional motions, and in several cases showed no reduction in displacement at all. Overall, the effectiveness of the gap damping system was less than what we anticipated from analysis, but we have a few ideas of what might have affected performance. In this next clip, we take a look at one of the simulations in which there was no reduction in displacement with gap damping, and that was the Chile record 100% in XY. On the left, we show the motion of the gap damper. On the right, we show the isolator time history, base isolation in blue, base isolation with gap damping in red. There's several cycles of damping activation here. Here we trigger another set of cycles. Yet no reduction in displacement. In fact, For base isolation, peak displacement was 5.27 inches, 5.37 inches with gap damper. One aspect that we believe influenced the effectiveness of the gap damping system was the axial forces on the isolation bearings. For the same Chile record, we show the axial force history being traced out in time with the isolator hysteresis loop. And you see there's a tendency as the axial force reaches a peak in the positive or negative direction, it's in line with a peak displacement on the hysteresis loop. And at some of those peak displacements, we see significant degradation in the hysteresis loop that's indicating that the isolators are reaching their stability limits. So the damping system increased overturning and axial forces on the isolators, causing the isolators to reach their stability limits. This next slide illustrates the comparison a little bit better. For the gap damper shown in blue, the base isolation alone shown in red. We see, with the axial force histories shown on the left, that the peak axial forces or peak compressive forces for the gap damper configuration were increased quite a bit compared to the base isolation configuration. Likewise, on the right, we see degradation in the hysteresis loop for the gap damper system relative to the base isolation system. We also noticed that the bearings appeared to be softening throughout the test program. As a result, we did a few extra base isolation repetitions at the end to assess if the bearings were changing over the course of the test program. This shows repetition 1 toward the beginning of the test program in red, and repetition 2 towards the end of the test program in blue. And you can see, based on the hysteresis loop, there was a significant softening of the bearings, and as a result, larger displacement demands. So certainly this had an influence on the effectiveness of the gap damper, because the softening of the bearings was counteracting the displacement reduction that we were trying to achieve with the gap damper. This completes our overview of the recent gap damper testing completed at the NEES UNR Earthquake Engineering Laboratory Shake Table Test Facility. We would like to again acknowledge the NSF grants for which funded this research, CMMI 1100922 and CMMI 1101105. We'd also like to acknowledge the lab staff that were instrumental in the smooth execution of this experiment. And finally, the data from this project will be permanently archived and publicly available in the NEES project warehouse under project number 1080. We expect it to be available within a couple months, summer of 2014. Thank you for your attention.